Hello, I'm Yihong, and we are Team 4, and our project is about seizure detection systems based on EEG data analysis and machine learning. So today we're going to talk a bit about the background and motivation behind our project, how we did our data preprocessing, our models and results, discussing our results, some actual applications of our project, and our conclusion. So first, let's get into some background and motivation for this project. So an EEG or an electroencephalogram is a measurement of the brain's activity. And as the global population ages, an increasing number of individuals are expected to experience neurological disorders such as memory loss, epilepsy, and attention deficits. Among these, epilepsy presents a particularly high burden, with millions of individuals worldwide suffering from seizures. So today, we want to present a model that detects seizures using EEG data and analysis.
The data set that we used was from the American University of Beirut Medical Center, and it was EEG data collected from six focal epilepsy patients during pre-surgical evaluation. Uh, they recorded 21, they used 21 scalp electrodes in a 1020 system, and the recordings included the interictal phases as well as the ictal phases. It also included data on the type of seizure as well as the ictal onset zone and seizure durations. The data was sampled at a frequency of 500 hertz and pre-processed with a bandpass filter and a notch filter. The data was then stored in the European data format. This is an example of a visualization of a patient's EEG data. Originally, the data set was formatted in this fashion, where they were labeled 0 through 3, because there were four types of seizures that were collected. And we formatted the data in a way that labeled the data as either normal or lesional, so abnormal. We then classified the data size into 19 by 500 matrices, the 19 representing the 19 electrodes and 500 for 1 second for the 500 hertz. We had a total of 7,790 matrices, and we split this data set into a 90-10 train test split and formatted using NumPy and MATLAB.
Uh, and now, due to brain signals are very complex data, we use different data visualizations and pre-processing methods to understand those signals. And for the pre-processing, we have used a famous MNE Python library widely used in the neurotechnology field to reshape, transform, and analyze the EEG data. Next slide, please. For the data transforming and labeling, we decided to a binary classification. So previously, the given data was labeled by 1, 2, 3 into a different seizure types. We combine into the one class, which is having a seizure patient, and class 0 represent the non-seizure normal states. We split into training and test data into 90% to 10% ratio, and we transform the 7,011 uh, data test samples and 19 EEG channels and 500 timestamps, which is a 1 second window size, into 19 channel and 500 and 7,011 to make it flattened to make it usable for the MNE library compatibility. And there's 19 channels total. Next slide, please. This slide shows the time series plot for the first patient EEG data, and in which it shows the first second, which is 500 timestamp for channel 1 to channel 19, including the FP to the occipital lobe. Next slide, please. We have also tried the power spectrum density since it's a non-stationary signals, and it shows the power changes across the frequency bands for each channels. So as you can see, there's 19 channels in the graph from hertz 0 to 40 hertz, which is covering most of the alpha through the gamma and all the signals from the brain. Next slide, please. This slide shows the time frequency representation analysis. We have also tried a Mole's wavelet transform. Mole wavelet transform can also capture the time location dependent data because frequency free Fourier transform does not capture the time dependency signals. We have also used the MOLET and wavelet transform to understand the complex brain signals. Yeah, and we also have shown this kind of heat map to show the time frequency analysis. Lastly, we have tried the correlation map, and this correlation map show the pairwise correlation between the different channels, channel 1 to channel 19, and the more red the show it have a higher correlation, as you can see the diagonal ways, and the more blue does show it does have is not related between the channels, and this shows the functional brain connectivity patterns. Next slide, please. Noise remover was already applied in the data set, so we do not have to apply it, but usually 50 Hz noise filter is applied for the power band, and the bandpass filter is used. And for the normalization, we have used for the machine learning technique, and we applied logarithmic normalization to improve the feature detection.
So going into our models and results. So first, we tried out an LSTM or long short-term memory network, which is, ideal for time series data because it can retain information over like longer sequences. And because this is basically a type of recurrent neural network or RNN, it can identify some of these complex features and maybe figure out some like time dependencies in the EEG data. So on the left, you can see the hyperparameters for the LSTM. And so these hyperparameters were tuned manually, and they were tuned to like limit overfitting and converge quickly to a loss or zero loss. And just to note some key things, the optimizer, we chose Atom because we initially tried stochastic gradient descent, but the log loss for SGD was around 0.693, which is basically random guessing for binary classification.
So here we have the results of the LSTM. You can see that the area under the curve here was 0.95, which is a lot better than if it was just left up to random chance. And the accuracy was 89.98%, which is pretty good. And if we look at the confusion matrix here as well, you can see that there were a lot more true positives and true negatives than there were false positives and false negatives. So overall, the model performed pretty well, but we wanted to see if we could get the accuracy a little bit higher.
All right, so the next thing we tried was a convolutional neural network or CNN. So CNNs are primarily used for images and image processing, but we wanted to test it out as an alternative to an LSTM. And so a CNN has spatial detection advantages, which can help maybe find out like some shapes in the signals rather than like the time dependencies compared to the LSTM. And again, this is a neural network, which should be a little more complex in determining the best features. And so something to note for the CNN is the activation function. So we used ReLU because it's like the most common activation function for the CNN.
And here we can see the results of the CNN. We can see that the area under the curve was 0.96 and the accuracy was 90.5%, which is a little bit better than the LSTM.
All right, so the last model that we tried was XGBoost because we wanted to try something that was not a neural network and it has the benefits of being computationally cheaper and more versatile because it's like a smaller hypothesis class. And so for XGBoost, we tuned our hyperparameters using Bayesian optimization. So after 100 studies of Bayesian optimization, on the left, these are the hyperparameters that we got for XGBoost.
So here's the results of XGBoost. The area under the curve was, again, 0.96, which is the same as it was for the CNN, but the accuracy was just a little bit lower at 90.24%. And if we consider that this is a lot computationally cheaper than the CNN, then this one performed pretty well.
So on this table below, or in this table on the slide, you can see the accuracies and AUCs are actually pretty similar across the board. But in our opinion, we thought the CNN performed the best just because it had the highest accuracy and it also had the highest AUC.
All right, getting a bit more into our results. So the convolutional neural network model ended up being the model with the highest accuracy. That may be due to the nature of how EEG data looks. CNN models are really good at image recognition, and since EEGs are signals, we, propose that CNNs are really good for analyzing signal data and time series data. But some trade-offs that we had to evaluate was what our prediction threshold should be. Because our model is trying to predict seizures, which is a medical condition. False positives and false negatives is a really important problem. We don't want to be alerting medical emergency services for a false alarm, and we also don't want to not catch a seizure that actually happens. And so the trade-offs was, should our threshold be high to make it a false positive more rare, or should we lower the threshold to increase the number of predictions at risk of having more false positives? Looking at comparative performance of our model, around a 90% accuracy is good. And we've demonstrated that with a pretty simple neural network, we're able to predict at high accuracy and show future applications for medical devices. However, compared to a recent study by the Princess Nora University researchers, this study achieved effectively 100% accuracy in Caesar prediction using more complex pre-processing and models. And so there still is room for improvement with our model, but overall, our results are pretty good. And lastly, some limitations with our model. The pre-processing decisions that we made were obviously human choices, so it's prone to error. Different choices could have led to different levels of accuracy. Also, with our data, it only captured 6 different patients with seizures, and so data scarcity was an issue that we dealt with. Training with more patients would obviously lead to perhaps a higher accuracy with our predictions. And an alternative solution to this that solves the data scarcity problem is using transfer learning. There are studies out there that are looking into how transfer learning can be specifically used for EEG signal analysis. And so there's more research to be done there.
Moving on to our application, we developed a prototype GUI using TK-inter to simulate real-time seizure detection. This application included features like signal visualization, as well as an emergency alert system for hospitals. Uh, the but however, there are several EEG technology limitations that prevent real-time seizure detection device development, such as the need for better electrodes, signal-to-noise ratio, and spatial resolution, as well as the lack of adaptive real-time systems for everyday use. The demo we created here is simplified, but we think it's an important step towards advanced medical monitoring technologies.
So yeah, just wrapping up our project. As you can see, previously talked about, there is a significant need for increased seizure detection technology, but it doesn't stop there. While we use CNNs to detect seizures in medical application, it would be much more useful to have real-time prediction almost, so that we might be able to treat seizures before they actually happen. And so while there's significant research going on in detection, we would like to see increased research going on in prediction accuracy. And that's what you saw in the GUI, just showing that our model was able to be adapted towards prediction. And yeah, we're hoping that with increased funding and research going into the BCI field and neurotech, specifically advancements in brainwave sensing and machine learning models, that these real-time advancements will become a fruition very soon. And then these were the sources that we used to research our entire project.